Classwork 2.1. So the first thing we are looking at is solving exponential equations where the bases of the exponential functions are numbers. And what they have in common is they are all dealing with a power of the same number. With 3 and 9, both of them are powers of 3. 3 is 3 to the 1 power, 9 is 3 to the 2nd power. So what you can do is rewrite these bases. 9 needs to turn into 3 squared, but you don't need to change 3 into 3 to the 1 because it already is. The next step is using this exponent rule. If you have b to the power of m to the power of n, recall, and what I'm about to write may seem like it doesn't need to be written, but if you keep seeing the picture that I'm drawing for you, if you keep seeing it over and over again, these exponent rules are going to stick better in your head. And that is, if I have b squared cubed, that's referring to 3 sets of 2 b's multiplying. And I want you to see that that creates multiplication between the two exponents. So you have to make sure, though, that you use the distributive property, because that 2 has to multiply by the entire exponent. Make sure you put a parenthesis around that 2x minus 3, and then distribute your multiplication over your addition or subtraction. And once you have those exponentials where the bases are identical, then it becomes a problem like you did in the last unit, where you just then set the exponents equal and solve and go, yay, done. And now let's practice. I've got 3 practice problems for you. Some of you are going to go a little bit faster than others. If we weren't online, you would be in your groups and you would be working together on each of these examples, talking about it with each other, using vocabulary. Online. What are we going to do? By the way, I will tell you, I've tried doing the whole putting people into groups. Every time I do it, it's a disaster. And with us already losing, literally we are losing a half hour for every class period. And so I'm struggling to just get through everything that I need to get through with you. And have you understanding, hopefully, because this is going to get more challenging as we go along. But if you learn a particular work habit with this class, I've got a lot of stuff written up to help you out. And don't forget that I have office hours from 2 to 3 p.m. I have a link to them. However, today I'm not going to be in them because I'm going to be busy trying to copy these packets. And I'm kind of going to assume that no one's going to want to show up right before a 4-day weekend anyway. Am I right on that? I don't know. But I'm going to be busy trying to finish copying these packets so you can pick them up. All right. I gave you a little bit of time to see if you could start the first problem. I don't know if you realize that. So now, if you look at problem number 2, look at the base numbers. And do you see that both of those numbers have a common base, shall we say? They are all some specific number to a power. Now, 2 really can't be broken down. 2 is 2 to the 1 power. 8 is 2 to what power? And I want you to, oh, I see some chat. There we go. So put in chat what the exponent needs to be on the 2 so that you get an 8. Bingo. For the classwork that you turn in, the first thing I need to see is this example written down, these 3 examples. So if you're just writing on paper, do that.
So why would it be a 3?
Okay, so, and this is why Unit 2 is actually something that I created to finish some things in Unit 2 that I felt a majority of people weren't quite ready for, and to make sure that you understood a few things. So here we go. I am going to create a little table, and actually I'm going to move way over here to the side to create it, because you guys need to be familiar with certain number patterns. I'm just going to do these. And so here in the first column are bases. And then I'm going to write that base squared, that base cubed. And some of these I'm not going to go too far. And I'll let you know about how far you need to be familiar with the number patterns. For 2, you need to be familiar with it all the way out. 2 squared is 4. If you multiply 2 another time, 2 cubed is 8. Let me just make sure you're clear. And then 2 to the 4th is, we can take what we already have with 2 cubed and multiply by 2 one more time to get 16. And then multiply 16 by 2, and what number do you get? You got it. So I want you to, or you want to be familiar with this number pattern. And in fact, that particular number pattern is really important in computer science. Computer science does a lot with binary numbers, and these are very, very special binary numbers, or numbers pertaining to binary. So let's now move on and look at 3. What is 3 times 3? I am continuing to get scam calls. Okay. What is 3 times 3? Someone can type it in chat. 9. Multiply by 3 again. Good, 27. Multiply by 3 again. 81. I'm going to stop there with the 3s. Any more than that is just getting out of hand. And by out of hand, what I really mean is I wouldn't expect you to have it memorized, but you could, with a calculator, deal with it. These number patterns you really want to be familiar with. It will save you a lot if you recognize these patterns when they show up. If you don't have them memorized, you can still get through things. It's just, it's going to take you longer to notice what to do. Now, what is 4 squared? 4 times 4. And then multiply by 4 again. What is 16 times 4? Be familiar there. I'm stopping there. That's that really is plenty right there. And then 5. What is 5 times 5? And then multiply by 5 one more time. Right. Be familiar with these number patterns. Spend time looking at them. You're going to be playing with them throughout this unit. And now that I've gone over those number patterns, if you look at 3 and 4, do you see those patterns that we were just looking at a little bit? Okay, now let's finish number 2. 2 is already 2 to the 1. So on the right side of this equation, I can just keep it as it is. 8, I'm going to put a parentheses where the 8 is. And then replace that 8 with a 2 to the 3rd power. Then I use the exponent rule of when I have a base to a power to a power, I multiply the exponents. And once the bases are the same, I can set the exponents equal. And at that point, you can solve the way you know how to solve. I'll distribute the multiplication of 3 over the addition. And then I will subtract 2x from both sides. And subtract 3 from both sides. And we've got a solution. Now, number 3 takes us into another area of an issue. I want to start off with 25 is equal to, and you want to recognize it as 5 squared. One over 125. I'm going to first write that if I want something in the denominator to be in the numerator, I make it a negative exponent. So I'm going to first write 125 to the negative 1 power. And by the way, if you can do these faster than I'm doing them, feel free to. And then 125 is 5 to what power? And I'm looking in chat. 125 is 5 to the 3rd power. So 1 over 125 is 5 to the power of negative 3. When I go to solve number 3, I'm going to rewrite each of these where I have a 25, I'm putting parentheses. And then over here, I'm just going to do a parentheses. No, I don't really need to. So 25, I'm replacing that with 5 squared. And the reason I'm saying parentheses is so that you see that you have to, with the exponent x, you have to multiply the 2 and the x together to get 5 to the power of 2x. And then this doesn't have an exponent on it. That's why I don't really need to write a parentheses. And I can just rewrite it as it is 5 to the negative 3. And then, once I have exactly the same bases, I can let the bases cancel each other out as an operation. And when they cancel each other out, you're left with their exponents being equal. Divide by 2. And then we've got one more example. I'm going to erase to make more room. And then you need to recognize we have 3 as a base. '81 is a power of 3 number. 81 is 3 to what power? Mm-hmm. 81 is 3 to the 4th power. So what does that mean 1 divided by 81 is? It is 3 to the, you got it, negative 4 power. Now I want to say something for just a moment. I want you to know that by doing these problems and really thinking about what you are doing, you are prepping for logarithms. Logarithms is, I want logarithms to go smoothly for you. That's what's going to be our unit 3. And in order for them to go smoothly, you actually need to get accustomed to the number patterns I'm talking to you about, get accustomed to the issue of what a negative exponent actually means, and play with these a little bit. And also, I've got some simplifying square roots coming up in some future classworks, because I've come to find that these are things that need to be strengthened before you do logarithms. So, can you finish number 4? Subtract 1 from both sides. And yay! So take a look. It's not too bad, is it? It's not too bad. Now, you have seen these graphs before, but how much do you actually remember? So instead of throwing this in the middle of Unit 1, I thought it would be good for you to focus on remembering how to graph lines in the previous section, in the previous unit. Remember how to graph parabolas, graph square root functions, and those absolute value functions. You still need to graph all of those. You need to retain that. Now, while you're retaining that, we're bringing in some old functions that you may not remember. Now I'm focusing on exponential growth today. Another day I'm going to focus on the decay version of exponential functions. When you have an exponential function, the base is a number and your variable is in the exponent. And you worked with these back in Math 1, but for some of you, that was over 2 years ago. And retaining things over 2 years is not high. Now, I want to emphasize that the number we will be using for the base is only going to be for numbers that are larger than 1. That is what will create growth. If you are investing money, you want to have a base that is greater than 1. If you're trying to invest money and that number goes under 1, you are losing money. And that can happen when money is invested in the more risky things. But when you put money into really, really carefully, your B is not going to be a large enough number to keep up with inflation, but it will be greater than 1. And it depends on where your safety feel is for that issue. And just to let you know and remind you of some things that you've learned about before. When you are dealing with investing money, that B number is always 1 plus your interest rate. And that rate written as a decimal number. So if you are investing money and you're investing it at a 2% interest rate, that means 1 plus 0.02. And that's a number bigger than 1. But if you lose money, you end up having to subtract that are getting a number less than 1. So I just want to kind of put into context with something you are familiar with or should be familiar with anyway. Now we're going to get to just the numbers. So what is 2 to the negative 4 power? It is 1 divided by what is 2 to the 4th power. And I want to get you to thinking these, I want you to type this in. 2 to the 4th, there we go. So 2 to the negative 4 is 1 over 16. And you know, while we're at it, how about we do 2 to the positive 4? And not have to think about that a second time. Then what is 2 to the negative 3 power? You got it. It's 1 over 2 cubed, and 2 cubed is 8. And I'm going to write it down there since we're talking about it. What is 2 to the negative 2 power? Good, 1/4. And 2 to the second power is 4. And what is 2 to the negative 1? Because you can just think about those exponent rules. Exponent rule just says you belong on the other side of the fraction. 1/2. What is 2 to the 0 power? Do you remember that? Any number to the power of 0 is 1, because you're saying don't multiply it ever. And the single number that is always a factor of everything is the number 1. Because anytime you write down like 5 is 5 times 1. -8 is -8 times 1. Everybody has 1 as its factor. And that's a bit of where that comes from. And then what is 2 to the 1 power? Now, what I want you to do is, as best you can, plot some of these points. Some of them are off grid and some of them are just too challenging to plot almost. I'm going to actually start by plotting at 0. And let me see. So I have the point 0, 1. And then I'm going to plot the point 1, 2. And then 2, 4. 3, 8. And I can't plot when x is 4, it goes off grid. So for the right side of the graph, it is growing. And on the answer key, I have a nice computer designed function for you to look at. Now, let's go backward and plot some of these. -1, 1/2. -2, 1/4. And then they're going to get tricky. 1/8 is a bit difficult to plot there. 1/16 is near impossible to plot and see that it's actually positive. But one thing that I want you to really notice, and this is very important, these numbers are positive numbers. The exponents that you see going in are negative. But a negative sign in an exponent is not the same thing as what you think of when you think of a negative number. When you see a negative sign in exponent, this is very crucial, very crucial, very crucial. Listen carefully. When you see a negative sign located in an exponent, you want to interpret it as reciprocal, or wrong side of the fraction, you need to move to the other side. Now, when I'm dealing with negative numbers themselves, there's a positive side of the number line and there's a negative side of the number line. The negative numbers are on the, quote, wrong side of 0, shall we say. A negative exponent says you're on the wrong side of the fraction and you need to move to the other side. Now I want you to notice that these numbers are going to stay positive But if I continue to let x go down to -6, -7, -8, -9, -10, those positive numbers are going to be impossible to plot. But you know that they are positive, which means they are located above the x-axis. That is very important, above the x-axis, these numbers. And what you need to understand very importantly is that if I take this table and I look at x equals -5, -6, -7, these will continue to be above the x-axis, but they are going to be closer to the x-axis. Now, this creates a particular feature of a graph. Does anyone know what the word is for this feature, this heading to a line feature?
Is it exponential growth?
That would be the name of the graph. And I don't know if you've heard this actual word before. Have you guys heard the word asymptote before? Does it sound familiar? You're going to need to get used to that word in this class. A lot of functions we're going to investigate in this class are going to have asymptotes. And take a good look at the spelling, asymptote, and we just say asymptote. We get a horizontal asymptote. And an asymptote is a line that a graph is getting closer and closer and closer to without being able to actually reach it. Now, admittedly, this is where math gets a bit theoretical with the idea of closer and closer and never being able to reach. When we look at the exponential decay model in a later time, if you remember the idea of like the whole carbon dating and having the, what is it called? Why can I not think of my words right now? I don't want to say the wrong phrases, but those isotopes and having, they go through an exponential decay.
You talking about like a half-life?
Thank you, yes. When we do the decay model, we're going to be looking at what this is a little bit more. But understand that the issue of it getting closer and closer to zero but staying positive is the same idea as the half-life issue. Now, the y-intercept is the point 0, 1. The domain, you can put any number you want in an exponent, but you cannot in the range. I want to emphasize a number line next to the range. The number 0 will never be in the y column. Never. That means the range does not include 0, but it includes every positive real number as close to 0 as you can imagine, and then closer than you can imagine, but only positive numbers. And so when I write the range, I want to first say that when you do interval notation, you write the left end is 0, the right end is infinity. Infinities always get the round brackets. But when a point is not included, it also gets a round bracket. When we were working with y equals x squared, the range on y equals x squared included 0. But this time it does not. And the growth as x approaches positive infinity is that f of x is going to approach positive infinity. As x approaches negative infinity, f of x is approaching 0. And then asymptotes come with equations. The horizontal asymptote is the equation y equals 0. And keep in mind, the asymptote isn't part of the graph, but I guess it's kind of like crutches. It's not part of you, but it helps you to walk. So it just is a way of that math people will draw to explain the behavior, to explain that the graph gets closer and 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 closer, but never will reach it. Now, I want to point out to you, if you have a general exponential growth, if you have the function a number to the power of x, that number is greater than 1. You will, when x is equal to 0, you will have b to the 0 power, which is 1. When you plug 1 into x, you get b to the 1, which is just plain the number. That is the base. When you graph exponential functions, I want you to plot 2 points. One of the points is the y-intercept. For the other point, you're going to plot the coordinate 1, b, whatever the base is. And then the growth goes la 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 and asymptoting. And again, on the typed notes, I have a computer-generated drawing for you to look at. So very important, very important, very important. Know these 2 points. And understand that in the next unit, we're going to do logarithms. Logarithms are the inverse of exponential. You have to understand exponential and be familiar with the points that it creates to be able to deal with logarithms. I'm sure you've probably heard, most of you have probably heard about logarithms, and I'm going to guess you haven't heard good things about it. But I very strongly feel that you need to be prepped for logarithms before being thrown into the pit. And by prepping you for them, that basically means taking all the snakes out of the pit before throwing you in. Do you like the metaphor? Yeah. Okay, anyway. So, important features. Know that the y-intercept every single time is the point 0, 1. The domain is always negative infinity to infinity. The range is always 0 to infinity, regardless of what the base greater than 1 number happens to be. As x approaches infinity, again, f of x approaches infinity. And then as x approaches negative infinity, f of x approaches 0. And the horizontal asymptote is y equals 0. So we now have 3 examples, and I believe we still have, how many? Okay, we're in second period. Second period gets out at 10:50. Am I correct? Okay, we're doing good. This is all that's left. And I want you to know that for quite a while, I am going to continue to give you graphs in this way, where I start off with a parent graph, and then I put in multiplication or division, and then I take that multiplication division and bring in addition subtraction. So if I ask you to graph a parent exponential growth 3 to the power of x, you can plot that the y-intercept is 1. And what point did I tell you to always plot? When x is equal to 1, the y-coordinate is the base. So you're going to plot the point 1, 3. And this will allow you to see the difference between the graph of 2 to the x versus 3 to the x versus 4 to the x, and so on. They all, however, do their asymptote business on the left end and grow like crazy, crazy, crazy grow on the right end. Now we have 10 minutes. The y-intercept is 0, 1. The domain, the range, and the horizontal asymptote. And I want you to write the equation of that horizontal asymptote. When I multiply a function by a number, all it's doing to the graph is taking the y-coordinates and doing exactly what that says, multiplying them by 2. So you keep them at the same x-coordinate that you see the points at, and you just take the y-coordinates that you do know and multiply them by that number. So y-coordinate 1 times 2 y-coordinate 3 times 2 and that's enough. From there, you should know that if all of these are positive numbers that are really small, when I multiply them by 2, they are still positive numbers that are really small. Now, when you are drawing, instead of letting a computer draw for you, you are not going to be able to graph perfectly. And I know that. What I want to see is that you have some understanding of how the graph is morphed. Can you see that when you go from that first graph to the second one, that you see kind of a stretch? Can you see that as, okay, this is an awful metaphor, but I feel like it's the most descriptive. if I take this exponential function and I put it on a medieval torture device where it stretches, you know, where they tie hands and then stretch, that's kind of what we're doing with this. Now, I want to point out that for the next function, you see that 2 times 3 to the x plus, or you see that 2 times 3 to the x. So we've already stretched. Now we're going to take that stretching and we're going to move it. And I know that you're familiar enough with the movement that you can look at this and see when x says +1, that means you're going to move left 1. When you see outside the function, not to the x, but to the function, -5, you know that means down 5. I want to point out, when you look at the x plus 1, you see +1, but what you're really doing is -1, aren't you? I just want to point this out, and by the end of Unit 2, I want to get you to a point where you actually have a bigger understanding of what is happening. When an operation occurs to x, you have to do the opposite operation on the graph. A way you can look at it is if you start with a graph, anything you do to the function after the function has taken place is done in that order, in a forward order, and it affects what the y coordinate is after the x has been plugged in. It's like going forward in time. But when you take a graph and you change what goes in before that function is actually able to occur, you're almost going backward in time. And to go backward, you have to do the opposite operation of what you see there. You see a +1, so you're actually going to do a -1, and it's affecting the x, so you do that horizontally. And I'm going to repeat all of what I just said a few times as we go through this unit. So then I am now taking the graph after I've done the multiplication. I'm taking the points that I know, and I'm going to put them as really light dots over here. I'm going to take those known points, and I'm going to move them. Left 1 down 5. And then left 1 down 5. Now the horizontal asymptote. Moving it left 1 is silly. You're moving a line that's horizontal to the left. It's still there. The down 5 tells you where that asymptote goes. That asymptote is down at -5. From there, draw this picture with that having been moved. You are not going to draw a perfect picture. I don't expect a perfect picture. I just want you to be able to show me visually what has happened. Now, to finish this up, I need to fill in the blanks under the bottom. When I did the stretching, I want you to see what changes and what doesn't change. The y-intercept changes when you stretch. and it happens to change to whatever number is multiplying to the function. The domain remains negative infinity to infinity. The range remains 0 to infinity. As long as I multiply by a positive number, the range will not be changed. And think about why that is. If the range is just positive numbers only, and I multiply them by positive numbers, I end up with positive numbers. The horizontal asymptote isn't changing. The only way your horizontal asymptote is going to be different is when you have a vertical movement. Whatever number you see adding or subtracting here, y equals that number, that's your horizontal asymptote. When I move the graph around, I don't change the domain. It's still negative infinity to positive infinity. But the range is changed if I have vertical motion. I move down 5, so the range is now from 5 to infinity, but it does not include the number 5. And that's it.